Okay, so it's time for our second example problem concerning the matrix and how to analyze a mixture on a UV-Vis using the matrix. So as I said in the previous video, the mixtures do not have to be colored. Therefore, we don't necessarily have to be running them in the visible portion of the spectrum in order to analyze these mixtures, especially if they do not actually absorb in the visible region. So we can actually analyze a mixture in the UV portion as well. So these are colorless solutions that are probably a little bit like organics, right? So when I take a look at the matrix, um, and this analysis of a mixture problem. This example is going to concern something that you've worked with already, and this is aspirin, and something else that you've worked with probably up to this point, and that's caffeine. So we're going to be analyzing a sample for both aspirin and caffeine at the same time, and you're probably wondering, well, would I actually ever have to do something like this? Well, especially in the world of pharmaceuticals, and the answer is yes, because if you take a look at the labels on some of the very common kind of pills that are out there, like Excedrin, for instance, you will see that Excedrin has multi-components. It's got a little bit of aspirin, it's got a little bit of caffeine, it's got a little bit of acetaminophen. It's got a couple of components that make up the pill that you take as Excedrin. So it's very common for me to take a pill, crush it up, and basically put it in solution and analyze that pill at the same time for all of the components that basically make it up. So if you've not chosen kind of your small scale research project with this semester, then this could be one of your idea topics, because we don't necessarily have a lab that focuses on extraction of pills and comparing maybe off-brand to the name brand, but that would be a very good choice for you to do. So we're going to be taking a look at a mixture of caffeine and a mixture of an aspirin. So basically, I need to bring you up to par. What's going to happen? Well, we've got this volumetric flask, and in this volumetric flask we have acetyl salicylic acid, and we have a little bit of caffeine, and we want to know what are the concentrations for each one of these. So what that means is that I need to take a volumetric flask and I need to make a standard. Well, I know that I'm going to be making aspirin, so I want to make an aspirin standard, right? And then I also know that I'm going to be looking for caffeine, so I want to make a caffeine standard as well. Okay, so there's kind of the first step that I have to take in this laboratory procedure if this is something that I need it to do. So take a look at your components, make standards of those components. Now, the question is, when I make this standard, what is the concentrations that I need to make? Well, in the beginning it doesn't really matter, right? And we said that this set of videos for this example problem is going to kind of start from the very beginning, and we're going to kind of work through piece by piece in order to get to the very end. So what are the concentrations of aspirin that I need? What's the concentration of caffeine that I need? Let's say that it doesn't give it to me in the procedure. How do I calculate this? Well, anytime I'm looking for calculating the concentration that I need to run on a UV-Vis, probably the equation that I need to use is Beer's law, A equals EBC, right? I need to make an aspirin standard that's going to be around 1 or lower, and I need to make a caffeine standard that's going to be around 1 or lower when I read it on the spec. So in order to do that, I need Beer's law to get that accomplished, right? This is the key. This concentration is what I want to know more about. So I know the path length, the molar absorptivity I can look up in the book, and the absorbance I kind of have an idea of what I want to do anyway. So let's come down here at the bottom and let's take a look at this Beer's law, and we're going to focus on aspirin in order or the first round at least. So I just want to make a 1 absorbance, right? It doesn't really matter. The only thing that I'm doing is just making sure that my molar absorptivity matches the book data. That's what I'm after. I want to make sure that those are really close numbers before I begin analyzing any type of mixture at all. So I go to aspirin and I look up the molar absorptivity in the text. And the molar absorptivity of aspirin in the book is 1288. Okay, so I'm going to put 1288 here for my E value. My path length is a 1 centimeter cuvette, and C is going to be the concentration. So I'm going to solve for C. And the way that I do that is that I take 1 and I divide it by 1288, right? Because 1288 times 1 is 1288. I need to solve for C. So you divide each side of the equation by 1288. And you're going to end up getting 7.76 times 10 to the negative fourth molarity. Okay, so this lets me know the concentration of aspirin that I need to make to run on a UV-Vis, and when I do that, I probably would get an absorbance close to 1. That's why I do Beer's law. So this gives me an idea of how much to weigh out. So molarity, then I would just go through and calculate the number of grams that I need. If I want to make a 100 mil standard or a 50 mil standard or a 10 mil standard, it doesn't matter. But you go take that number from that point, you convert that over to grams. That will tell you how many grams of aspirin that you actually need to weigh out to make the standard with. Okay, so that's the aspirin part. Okay, so before we go further, we're now going to be doing the caffeine part. So if I take a look at caffeine and I look that molar absorptivity up in the book, I'm going to get maybe 8510. And I go, okay, I need to make a standard to run on the UV-Vis, and I want about a 1 absorbance again, right? That's always kind of a nice clean number that I like to use. So 1 is equal to the molar absorptivity of caffeine from the book is 8510 times 1 times C. Okay, so in order to solve for C, which is the concentration of caffeine that I need to get a 1 absorbance, well, 8510 times 1 is 8510, and then I divide each side of the equation by 8510 in order to solve for C. Okay, so I do 1 divided by 8510, and I'm going to end up getting about 1.17 times 10 to the negative fourth molarity. Okay, so from this point, I can do the same thing that I did with aspirin here. This means that I need to make a 1.1 times 10 to the negative fourth standard of the caffeine sample. So I would convert that over to grams, weigh out that many number of grams, put it into my volumetric flask, dilute it to the line with water, shake and invert, and mix it really well. So I get these 2 standards now, an aspirin standard and a caffeine standard. And then the very first thing that I do, well, this is kind of number 1, right? So this is the number 1 thing that I do. Figure out the concentrations that you need to make. All right, so number 2, I'm then going to run the standards, STD, the standards on the UV-Vis. All right, and the purpose of running the standards on the UV-Vis is just to make sure that you get a 1 absorbance. Okay, so we're going to pretend that when we made aspirin, we were perfect, all right? So when we make the aspirin, we actually did make a 7.76 times 10 to the negative fourth molarity solution. That's what we actually made. But when we ran it on the Vis, we did not get a 1 absorbance. Okay, so let's say that we ran this sample, and we got a spectra for the sample, and it looks something like this maybe. And the very first thing that I'll look for is the hump. Where is the lambda max? So there's the lambda max. This is the wavelength that gives me the maximum absorbance. And this lambda max is showing up about 229. Okay, that's the nanometers. So at 229, I'm seeing a really strong absorbance. but I don't really get a 1 absorbance. Let's say that I ended up getting a 0.672 absorbance. Okay, so either number one, I really messed up making my solution, or number two, my molar absorptivity is off from the book value. And this could be maybe due to maybe the solvent that I'm using, maybe it's due to the instrument that I'm using, who knows what's happening, but I'm off. So I go back and I double check my calculations and it looks like I did everything right. I did the solution prep right. So it's just maybe something to do with the solvent or something to do with the machine. So the first thing that I have to do is go back and I have to recalculate the molar absorptivity. And I do that by using Beer's law, A equals EBC. So the absorbance that I got from here is 0.672. And the molar absorptivity, I want to just calculate to see what that number is now. Experimentally, the molar absorptivity number. B is the path length, well that's 1. And C is the concentration of the solution that I made. And we're going to pretend like we were perfect. And we're going to put 7.76 times 10 to the negative fourth molarity. So I solve for my E value, my molar absorptivity. So I take 0.672 and then I divide by 7.76 times 10 to the negative fourth. Be sure to put that in parentheses. And when you do that division step, you're going to get about 866 rounded off. That is your molar absorptivity. So we're off from the book value. And when you did your lab with the aspirin, you probably saw this happen to you as well. You didn't get 1288. You got something a little bit lower. And we had to use your corrected molar absorptivity that you got with your sample on your machine in order to do the calculations with. So 866 is the true molar absorptivity for aspirin that we will use in part of the problem. Okay, so we're going to stop here. In the second part of the video, we're going to focus on caffeine, and we're going to do the same thing that we just did with aspirin to caffeine. We have to calculate the true molar absorptivity that I should be using in this problem, not the book molar absorptivity. So stay tuned. Another video is yet to come.